Hello, everybody. Thank you so much for joining us this afternoon for our webinar on the New York State Science Test Prep. We're going to do some 3D item analysis and talk about strategies for student readiness. Thank you again to those of you who've been introducing yourselves in the chat. If you wouldn't mind, if you haven't done so, going ahead and introducing yourself, saying where you're from, what you do, that would be awesome. And while y'all are doing that, I'm going to go ahead and introduce myself, and my colleagues shall do the same. So my name is Emily Miller. My pronouns are she, her. Prior to coming to Inner Orbit, I was a high school chemistry teacher for 10 years in Minnesota. During that time, I taught in our alternative learning program. I taught regular chem, honors chem, so lots of different ways to teach a lot of different kids a lot of different ways. I worked a lot with the NGSS within my time in the classroom, and I also got to be a PLC lead, so I got to lead a lot of data-driven dialogue, which I love. And now I have the joy of partnering with districts to help them implement Inner Orbit. And speaking of the Super Bowl, I actually don't even know who's playing Super Bowl this weekend, so that is how in tune I am. And with that, I'll be going ahead and passing it over to Julia.
Well, that's fair, Emily. I'm not really sure of who's playing, but my name is Julia Mota. I was a teacher and tutor for elementary students in the Dominican Republic for quite a while, and I've been supporting teachers and districts with their NGSS implementation now for the past 4 years. So in my role right now, I've been partnering and providing guidance to schools and districts implementing assessment in their NGSS instruction. And I've worked with a lot of teachers in New York. I'm really excited for this webinar. I was honestly rooting for the Bears just because I'm in Chicago, and they made it far, assuming it wasn't such a great team. But yeah, we'll see what happens. I don't even know who's playing. I think the Patriots and the Seahawks, is it? I don't know. Do you know, Daniel?
Not sure, actually, but my name is Daniel Jackson. I was formerly a curriculum director, high school biology, and middle school science teacher for 11 years in education. I taught at an international school in Colombia. I was a global education and Fulbright TGC scholar in Morocco, and I currently partner with school leaders and teachers new to Inner Orbit. I like to say I'm a super fan of football, but just during the Super Bowl. Maybe I need to rewrite that because I couldn't answer or confirm who's playing today. But let's go over our agenda for today. Our goal is to cover the structure and the expectations of the New York State science tests, be able to identify the NIST dimensions within test items, and learn how scaffolded formative assessments can support student progression towards confidently answering 3D phenomena-driven questions. We'll be together for about 45 minutes. First, I'll go over and give an overview of Inner Orbit. Next, we'll cover the shift to sense making and talk through assessments that align with the elementary, intermediate, and region science tests. From there, we'll go over the New York science test structure and region item analysis, along with examples of scaffolded formatives from Inner Orbit that can help teachers prepare students for these exams. We'll also provide a helpful classroom resource for phenomenon-based questions towards the end. And as the wise Yoda once said, do or do not, there is no try. That's all I got from Star Wars. So with that, I'll begin with a quick introduction to what Inner Orbit is and how it supports educators. At Inner Orbit, we like to say there are three core components to what we do. We have phenomena, we have assessments, and we have detailed high-integrity 3D assessments at Inner Orbit are designed to provide meaningful and actionable student data so educators can make informed instructional decisions with confidence. We also make the NGSS accessible for both you and your students through innovative approaches to sense making. That means we don't just drop students straight into these complex theory questions. Instead, we use scaffolded prompts that move students from more basic, one-dimensional content-focused understanding towards those larger three-dimensional questions, which we'll talk more about in just a bit. And in addition to the questions themselves, we also provide supporting activities you can use with your students to help build that understanding over time so that they're prepared and confident when they reach those more rigorous summative assessments later on, such as on the elementary, intermediate, and region science tests. We also provide guidance, supporting resources, and professional development to help you reach your NGSS goals, just like the session we're hosting today. If you're interested in learning more about Inner Orbit, feel free to fill out that interest form, and from there, we'll share additional information and show you how you can try Inner Orbit within your districts. Next, I want to talk about the shift to sense making in regard to how we can interpret and proficiency when prepping for the New York State science tests. And if you've been teaching for years, you probably felt this huge shift already. Proficiency has moved from standards that often focused on isolated facts, content, or skills to performance expectations that describe what students should actually be able to do and to demonstrate understanding. Under the NGSS, proficiency is defined by sense making, which is when students integrate the three dimensions to explain phenomena and solve problems. not just recall information. Let's now take a look at what those three dimensions of the NGSS and NIST lists are. As you may know, the three dimensions are what sit at the heart of the NGSS and NIST lists. First, we have the disciplinary core ideas. These are the content, the science that students are learning. In this example, the DCI we're focusing on is adaptation. Students need to understand that in a given habitat, some organisms survive well, some survive less well, and some cannot survive at all. That understanding is a critical part of the content students are expected to learn, although on its own, that kind of recall is no longer sufficient to say a student is proficient. The second dimension is the science and engineering practices. This is what students are actually doing with the science. Practices include things like constructing arguments, analyzing data, and developing or using models. In other words, thinking and acting like scientists. In this performance expectation, students are asked to engage in argument from evidence, meaning they must construct a claim to support it with evidence based on what they've already learned about adaptation. And finally, we have the cross-cutting concepts. These are the big ideas that are connected across scientific disciplines. They shape how students think about science, and examples include patterns, systems, and cause and effect. In the example here, the cross-cutting concept is cause and effect. Students need to reason through how certain traits or conditions in a habitat cause some organisms to survive better than others. When all three of these dimensions come together, we get a much clearer picture of what students truly understand. We're no longer just measuring what they can memorize, we're assessing how they think, reason, and apply their knowledge. And that's the key difference with three-dimensional sense-making focused assessments. Let's talk a little bit more about sense-making. So when we say sense-making, we're talking about what happens when students pull together everything they already know, their ideas, their skills, and their experiences to make sense of something they don't fully understand yet. That process usually begins with a phenomena that's puzzling and raises questions. From there, students might use science and engineering practices to investigate. Maybe they ask questions, analyze data, or construct explanations, while at the same time drawing on disciplinary core ideas and cross-cutting concepts. As we can see in the image, sense-making isn't expected to be linear. Students won't always move step by step in a straight line. Instead, they can move back and forth between practices, content, and cross-cutting concepts as they refine their understanding. Rather than jumping straight to the right answer, they're working to figure out why something is happening. They're testing ideas, revisiting their thinking, revising their thinking, and asking better questions along the way. That's what really what the NGSS is aiming for, and what we believe strong assessments and strong instruction should be designed to support. Students that show proficiency are able to bring all of these pieces together to make sense of new or novel scenarios. Now that we've gone over sense making, I'll pass it over to Emily to show you how sense making is incorporated into the New York Science tests.
Thank you so much, Daniel. I always like getting that little refresher on just like what the different dimensions are and how they all play together before we start diving into all of the fun complexities of the structure of these state tests. So as you all are probably aware, we have got the elementary New York State science tests, the intermediate New York State science tests, and then the Regents exams. I'm going to be talking about the overall structure of all of these. And then the strategies we're going to discuss can be applied across all of these different tests. So for the elementary test, here's going to be the breakdown of the different content areas within it. For the elementary, there's a pretty even spread between physical science, life science, and earth and space science. Students are going to be given about 36 to 43 questions. And these questions are going to be grouped together by clusters. These clusters are going to be phenomena-based clusters. So there's going to be a new or novel phenomena that students need to make sense of. And there's going to be multiple questions about that one phenomena. This is elementary. So this is the elementary science test. We're also going to talk about intermediate, and we're also going to talk about the Regents as well. So this is at the 5th grade level, Then at the intermediate level, as you can see here, there's still a similar breakdown between physical science, life science, and earth and space. So everything is kind of evenly attributed here. At the 8th grade level, they're going to be asked a few more questions, and there's going to be more questions per cluster at the 8th grade level as well. Again, when we're looking at that cluster, we're looking at a phenomena, and all these questions are tied to that phenomena. This is a computer-based test, so students are going to be taking this on the computer. Approximately 60% of the test is multiple choice, and about 40% is constructed response, or TEI, tech enhanced items. Would be like drag and drop questions. Those would be multi-select questions, like putting different images like on a graph or on a picture, things like that. Like I mentioned, the questions are going to be grouped by phenomena clusters, and there's going to be no time limit on this, which is nice. So students are going to have as much time as they need in order to answer all of these questions and to take these exams. Now down to Oh, before we talk about the regions here, I wanted to show you a little bit about what it's going to look like on the computer for students. So as you can see here, they've got the phenomena over here on the left. And then on the right, students are going to be given the questions. So this would be an example of a constructed response where they need to physically go in here and type their answer. And then this would be a multiple choice where they would select the best answer. Notice how the phenomena, while it's still talking about photosynthesis and ATP, it's not always going to be necessarily the same images and text right next door. So students, as they're scrolling through, the phenomena may change or evolve, but it's all going to be tied to that same overall concept or idea. So there's going to be multiple questions about that same process. I also wanted to take a minute to talk about the performance level descriptors, or the PLDs. As you may know, these are like the written requirements that students need to do in order to earn a certain level on these state science tests. Our goal is for students to earn a level 3, so that would be proficient. And what I want to point out here is how the level 3, the proficient, really mirrors the actual standard that this question is assessing. So this question here is assessing MS-LS 1-6. And as you can see, both of these include a science and engineering practice component. So this constructing explanations and designing solutions. So students need to construct a scientific explanation based on evidence. They need to construct a scientific explanation based on evidence. Students are also going to be responsible for content in order to answer this question. So this idea that photosynthesis is the cycling of matter and the flow of energy throughout organisms. So they need to have the content in order to answer this question as well and get that proficient response. And then finally, the cross-cutting concept in this case is really similar to the DCI, where they have to big picture understand the energy and matter flow throughout this cycle. So in order for students to become proficient and earn that level 3, they are going to need to incorporate all 3 dimensions of the NGSS, of the NIST, of the standards in order to earn that PLD level 3. So that's kind of that shift that Daniel was talking about, where we're not just expecting students to understand content, but they need to be able to do the SEPs and the skills and understand the big scientific ideas as well in order to hit all of those requirements to earn that proficient level. Today, we're going to be talking about how inner orbit scaffolds questions in order to get students to be able to answer questions at a 3-dimensional rigor. And then we'll show you data that you can collect along the way to help support your students with those specific dimensions as well. Another thing I want to talk about with the elementary and intermediate before I go on to the Regents exam is something that we call cut scores. So as you can see here, we have the different scores that students need to earn in order to get a level 1, a level 2, a level 3, or a level 4. Personally, looking at this doesn't mean much to me as a teacher. So what we've done here at Inner Orbit is we've taken these computer-based like funky scores and we've translated them into percentages to kind of give us a frame of reference to see what students need to be able to do to earn that proficient level. So for example, at grade 5, the minimum score students can earn is a 398. The maximum amount of points they can earn is a 516. For the 8th grade tests, the minimum amount is 391. The maximum is 533. So doing the math for you here, there are 118 points that students could earn on the 5th grade test and 142 points that could be earned on the 8th grade test. Now, when we're looking at that level 3, when we're looking at that proficient, it looks like students need to get at least a minimum of 450 on both tests in order to get that level 3, which we consider proficient. So doing some math here, if students need to earn 450, it looks like they need to earn at least 52 points out of the 118 to get proficient on the 5th grade test. And they have to earn about 59 points to get a proficient on the 8th grade test. You can probably see where I'm going with this. So if they have to earn 52 points and there's 118 points available, if they have to earn 59 points on the 8th grade test and there's 142 points available, this comes out to be about 44% correct on the 5th grade test and 42% on the 8th grade test. Now, I don't know about you, but my teacher brain is programmed to see 42% and think that's failing. We are not where we need to be. But this is where we really like to take a moment to pause and think about this. They need to get about 42 to 44% of the questions right to earn a proficient. That is really different than that traditional ABCD scale that we expect our students to perform in our classroom. So when we're giving them these really rigorous 3-dimensional items that are phenomena-based, the standard to what we expect normally has shifted. So whether you're using Inner Orbit or you're using another practice tool, however you're trying to help prepare your students, keep in mind that 42, 44% for the elementary and the intermediate is actually what we're aiming for. So if students are getting about half of the things right, we're actually on track to get to that proficiency. Now, moving on to the Regents. So the Regents are the high school level New York State science tests that are content specific. So I'm going to be talking about the Earth and Space Science test and the biology test. Chemistry and physics, they're common, but right now we're just going to focus on these ones that have been given for a minute. So for the Earth and Space Science test, it's obviously all going to be Earth and Space Science. We do have a breakdown here of the different domains within Earth and Space Science. So space systems is about 30%, and then you can see from here. This test is going to be anywhere from 45 to 55 questions, and there's going to be about 9 to 11 questions per cluster. So just like the elementary and the intermediate tests, this is going to be a cluster-based exam. So there's going to be a phenomena, and then there's going to be multiple questions, 9 to 11, that are based on that same phenomena or idea. For the biology test, again, it's all going to be biology. But if you want a breakdown of the different types of biological topics that can be discussed, you've got the percentages here. This test is also going to be 45 to 55 questions, and there's also going to be about 9 to 11 questions per phenomena cluster. The Regents is a paper-based test, so students will be taking this on paper. But just like the elementary and the intermediate, about 60% of the test is multiple choice, and 40% is constructed response. So there's going to be a lot of questions where students aren't going to have that multiple choice scaffolding, and they're actually going to have to write out their own responses. Students will have 3 hours to complete the test, and this is pulled directly from New York State Government PDF about the test. Every question on the test will draw from all 3 dimensions: SEPs, DCI, CCCs, requiring students to demonstrate their knowledge and skills. So in order to help prepare students for this test, we really do need to move beyond just content, which is part of our standards, which we know, but it can be hard to implement it in practice, and it can be really hard to implement it in assessment, which is where Inner Orbit can kind of come in and help support that. Now, these are the scores for the Regents exams that were released actually just this past month in January. So for the Earth and Space Science tests, this is out of 50 points. The minimum amount of points they can get is 0. For the biology test, 45 is the maximum amount of points they can get, and then the minimum is 0. Now that cutoff between getting a level 3 and a level 4 is right at this 32 to 33. Which also reminds me, I should have mentioned this earlier, the Regents exam is actually on a scale from 1 to 5. So a performance level 1 being the lowest, and a performance level 5 being the highest. Elementary and intermediate is 1 through 4. Regents is 1 through 5, with a 4 being proficient. So that cutoff to be getting a 3 to a 4 is 32 to 33. And on the biology, the cutoff is getting a 27. So again, we're going to do the math here. So they got to get 33 points to get proficient on Earth and Space Science, 27 points on biology. If there's 50 questions on Earth and Space Science and 45 questions on biology, our proficiency is right around that 66 to 60%. Now, higher than elementary and intermediate. But again, I don't know about you, when I see 60 and 66%, I'm thinking D minus. So again, taking that shift, when we're giving these students these rigorous 3-dimensional questions, the expectation and that level of standard for proficiency is different than what we generally expect to see in the classroom. So to recap the structures of the different tests and the different expectations before we actually look at an actual item, the elementary and intermediate is on the computer, 60% multiple choice, 40% constructed response or TEI, and the questions are going to be grouped by phenomena clusters. And that proficiency is right around that 40-ish%. For the Regents, it's on paper. It's still 60-40 split. They have 3 hours to take it, and the proficiency is around that 66 to 60%. But the main takeaway I want to share with all of you here is that students are going to need to utilize all 3 dimensions in order to be able to answer questions proficiently on the test. And again, when we're thinking about 40% of them as constructed response, those test graders are really going to be looking for, have they incorporated all 3 of those dimensions within their written response answer in order to get that proficient score. Which leads me to, I want us to look at an Earth and Space Science Regents item. By doing this, we're going to look and see how the 3 dimensions are woven within the item, so we can see how students would need to apply all of those. And then from there, we're going to talk about how Inner Orbit gives scaffolded items to help prepare students to answer a question like this. So the Earth and Space Science Regents item we're going to be looking at is on the standard HSESS 27, which is about constructing an argument based on evidence about the simultaneous coevolution of Earth systems and life on Earth. Again, I want to bring this back to the PLDs. So for the Regents, we need to get that level 4 in order to be proficient. So when we are comparing that level 4 PLD to the actual standard, just ESS 2.7, students are going to need to construct an argument based on evidence. So that is the SEP, that is the skill. So students need to come up with an argument and they have to back it up with evidence. So that will need to be included. The content, the DCI that they're going to need to know is the coevolution of Earth systems and life on Earth. So how do the Earth systems and how does the life on Earth, how do they cause each other to evolve and change over time? Which leads to the cross-cutting concept of stability and change. This idea that we can come up with explanations for how things change or how things remain stable over time. So all 3 dimensions within the standard are going to be incorporated into that level 4 PLD, which we want students to get in order to be proficient. So let's go ahead and actually take a look at the item. So the phenomena that students are going to be referencing to answer the item that I pulled is all about stromatolites. I think I said that right. So this is talking about how the water in the Earth's early oceans actually provided the necessary life in order to start changing the composition of Earth's atmosphere. And we've got a nice little graph over here that's showing how over time atmospheric oxygen and carbon dioxide changed. So this is a constructed response question. Remember, about 40% of the test is going to be constructed response. And this is asking students to construct an argument based on evidence in the model about how stromatolites in Earth's oceans caused Earth's early atmosphere to evolve. You might remember the Yoda gif from earlier. I'm the Star Wars nerd in the group here. So this is a lot, right? So students need to incorporate those 3 dimensions in order to answer this question. So let's go ahead and actually see what that would look like. As a reminder, the SEP that students need to do here is engaging in argument from evidence. The DCI is all about the coevolution of Earth's systems and the life on Earth. And the cross-cutting concept is stability and change. So first, looking at the SEP, students need to utilize the SEP to answer this question because right away at the beginning of the prompt, it tells them to construct an argument based on evidence. So that is the skill that they have to be able to do. So the evidence that they're going to be pulling from is actually the evidence in the graph and in the model here. So they need to reference the graph and the model, extrapolate evidence from it, to then come up with an argument. So talking about how oxygen raised and carbon dioxide fell. The content that they're going to need to know in order to answer this question is understanding how stromatolites would have affected this change in carbon dioxide going down and oxygen going up. While reading the prompt, students could see that stromatolites were actually capable of photosynthesis. So this is going to take an understanding of how photosynthesis organisms or plants take in carbon dioxide and release oxygen. So understanding the components of photosynthesis and how these stromatolites were using carbon dioxide from the atmosphere and then releasing oxygen back out into the atmosphere. That would be the content they would have to know in order to answer this. Lastly, the cross-cutting concept is all about constructing explanations about how things are stable or how they change. So in this case, they have to still construct that argument, that explanation about how the atmosphere has evolved. So in this case, we're talking about how things can change over time. So you can see down at the bottom, we've got this billions of years ago. So we've got this really, really long time frame, and we're seeing how change occurred over this time period. So in order to answer this question, students are going to have to incorporate all 3 of these dimensions in order to earn the point for this question. And remember, they need to get about 66% of these questions correct in order to get that proficiency level of 4. It's a lot. It's a lot to throw students in here. Having them look at phenomena that they've never seen before. I don't know about you, but as a kid, I might have seen that and been like, what's a stromatolite? What? And then I would have just been like, I'm over it. So giving students exposure to phenomena and giving them exposure to questions that build up to that 3-dimensional rigor will help equip them with the skills they need in order to answer questions like this on their own, on the Regents, or on the elementary or on the intermediate. Like we've talked about, there's been this shift of going from just knowing content to doing sense making. But as Han Solo said, never tell me the odds. We can totally do the Kessel run in 12 parsecs. I'll show you how we do it. On inner orbit, what we've done is we've written questions in a way, like I said, that slowly scaffold to that 3-dimensional rigor. So rather than going from what is the powerhouse of the cell to construct an argument based on evidence, we've created these in-between points. So on our site, the first type of question that you're going to see are 1-dimensional content only questions, like what is the powerhouse of the cell? Now we need to move on from this, but this is a starting point because we still need to have students know what photosynthesis is before they can start adding those other dimensions. Now, the other type of question we've written on our site are two-dimensional questions. These are really unique in the way that there's still content involved, but now we're either incorporating the SEP or the cross-cutting concept. Give students a chance to practice these skills individually, and it also yields interesting data to teachers on if there's one of these dimensions that students may or may not need more support with before we eventually can give students a three-dimensional question, which, as you saw, we need to be able to answer three-dimensional questions in order to be proficient. Because if we can utilize all three of those dimensions, we're at that PLD level 3 or 4, and we're at that proficiency. So the inner orbit example that I'm going to show you that could scaffold to that three-dimensional rigor is the exact same standard that we just looked at with the stromatolites. In this case, though, the phenomena is all about different organisms in the ocean. So this is talking about the great oxidation effect. So kind of what the stromatolites were talking about, but we're looking at different organisms over time. So this would be the phenomena on inner orbit that students would be referencing to. And here is an example of a question that we have on inner orbit. Increased oxygen in the Earth's atmosphere could lead to, all these phrases are correct. But what I want to ask all of you is, we're talking here about how we can scaffold questions. So we're talking about how we can slowly lead students to three-dimensional rigor. So while we're on this journey to three-dimensional rigor, looking at this question, do you think this question is a 1D, a 2D, or a 3D? You can type it in the chat, or Julia just launched a poll for all of you. So on the poll, you can go ahead and select, do you think this question, increased oxygen in the Earth's atmosphere, do you think this is 1D? Do you think this is 2D? Or do you think this is 3D? I see some people responding. Thank you so much. Awesome. We'll give it another like 10 seconds or so. All right, here we go. There we go. Sharing the results. So we have a split between 1D and 2D, and we have one 3D. I love having these conversations and doing these polls because it always gives me some interesting insights as well into the different questions we have. This question here on inner orbit, we've actually flagged as 1D. One-dimensional. We flagged this as one-dimensional because if you remember, the DCI, the content knowledge, is all about this coevolution. So this idea that life on Earth can affect Earth's systems. So this is talking about how increased oxygen in the atmosphere, how could that affect other living things on Earth? So it's talking about how those two things can interact with one another. Now, if some of you were thinking 2D with the CCC with stability and change, sometimes those overlap. The cross-cutting concept and the DCI, that overarching idea is really similar to the content. But in a minute here, I'll show you a 2D CCC question and we can see how they're a little bit different. So this is a first step in helping scaffold students up to be able to answer that rigorous three-dimensional question we saw in the regions. Now we're looking at the same phenomena because this is a cluster, but now the question is, refer to figure 2. Between 1 billion to 2 billion years ago, the concentration of oxygen in Earth's atmosphere would be best described as, do you think this is a one-dimensional, a two-dimensional, or a three-dimensional question? We've got the poll back up, same options as before. Thank you so much for answering. All right, maybe like 5 or 10 more seconds. We have much more of a consensus on this one. There we go. Two-dimensional. So as promised, here's a two-dimensional CCC question. So this is still looking at the idea of the content about how oxygen in the Earth can change and how these things interact with each other. But now we're specifically talking about stability and change. So in this case, they have to construct that explanation. So they have to like be able to explain the stability and change by referencing these different materials over here. So again, we're slowly scaffolding students up to be able to answer those three-dimensional questions. So understanding coevolution, now we're understanding how we can like look at graphs and pictures to understand stability and change. Another question, consider the reactants and products in figure 3. Which of the following is the best argument about the impact of simple cells on Earth's systems? Is this question a one-dimensional, a two-dimensional, or a three-dimensional question? What do y'all think? All right, thank you again for answering. All right, another 5 or 10 seconds or so. All right, on our site, we have classified this as a two-dimensional question. So with the DCI and the SEP. So a lot of people said three-dimensional, but if you kind of look here, we're still not talking about that overarching idea of stability and change. This idea that things on Earth can become stable or they can change like over these like long courses of time. So here we're more or less looking at this idea about which is the best argument. And this is all about engaging an argument from evidence. So they could go back, they could look at their evidence here and then find which one of these could be that best argument for that. All right. Again, we're talking about scaffolding, right? So we're at the two-dimensional. Now here's another question for you. Refer to figures 1 and 2. Which claim is best supported by the available evidence? Do you think this question is one-dimensional, two-dimensional, or three-dimensional? Thank you again for answering. Give it about 10 more seconds, 5 more seconds. All right. So we're a little bit more split on this one. On our site, we have categorized this as a three-dimensional question. So first, we're being asked which claim is best supported by the available evidence. So that's our SEP, engaging in argument from evidence. We're talking about oxygen levels and how they would have affected evolution. So we're talking about that Earth's atmosphere and its effect on life forms on Earth. So that's that coevolution, that's that DCI. And then what we're talking about here, again, is this idea of evolution of change over time. So this stability and change over time. So needing to look at and see how the amount of oxygen has increased, and then looking and seeing how the amount of different animals over time has changed as well. So we flagged this as a three-dimensional question. Again, we're still talking about the scaffolding, and I got one more question for you. Using evidence from the figures and text, construct an argument that supports the coevolution of Earth's biosphere, hydrosphere, and atmosphere over billions of years. Be sure to include descriptions of changes and/or stability in your argument. So what do we think? Is this a one-dimensional question, a two-dimensional question, or a three-dimensional question? Thank you again for answering. About 10 more seconds. More of a consensus on this one. This is three-dimensional. And if you remember the Regents question, construct an argument based on evidence about how stromatolites changed Earth's atmosphere over time. Use evidence from the figures and text, construct an argument that support the coevolution of Earth's biosphere, hydrosphere, and atmosphere over billions of years. So answering a question like this mirrors kind of what students were expected to do on the Regents. And if we give students these questions incrementally over time, or give them all of them at once and have a classroom discussion about how these questions have changed and the rigor of them have changed, however you want this to look in your classroom. But what we can do here is understand, do my students understand the content? Do they understand how organisms on Earth and like the systems of Earth, how they can affect one another? Do they understand how things can either change or be stable over billions of years? Do they understand how to construct an argument from evidence? Can they do that together if I give them a multiple choice response? So I've got a little bit of scaffolding in there. There's some answers. They can look for the best one. They can get rid of them before I actually ask them to independently construct a response all on their own. By giving students questions in this progression, one, not only are you getting data along the way to help you understand how they're doing with this progression, but two, you're offering assessment scaffolds in place to get them to eventually be able to do that larger constructed response question on their own. So I want to show you how you could find formative assessment, a scaffolded formative assessment, just like the progression we went through on our site. So let's pretend you are teaching New Visions, the New Visions curriculum, and you're doing Earth and Space Science. Let's say you're in the unit of probability of life elsewhere, and you just covered the same standard of HSESS 27. You can go onto our site, and we actually have curriculum guides for different curricula. That does not mean you can't use our site if you don't have these. You can use our site and just search by keyword, by key phrase, by standard. But if you're using one of these curriculum, it's a little bit easier. You can go to New Visions. You can select Earth and Space Science. You can select the current unit that you're teaching, and you can click our pre-made formative assessments. And right there, you can find a pre-made formative assessment that will have one-dimensional, two-dimensional, and three-dimensional questions in it, just like the different questions that we looked at. So you can give students those scaffolded questions so they can start building those skills over time. And then you get the data along the way to help see what they might need help with. Now, in just a moment, Daniel's going to show you examples of that awesome data that I keep talking about. But really quick, Julia is going to drop in the chat again a link to our interest form. This interest form is essentially you letting us know that you're interested in piloting and trying out inner orbit. This is not a commitment. You are not like writing your name. I was going to say blood. That's a little gross. So you're not writing your name. And I just said it. I shouldn't have said it. This is no commitment. That's what I'm trying to say. You're just letting us know that you're interested, that you want to learn more. We'll go ahead and shoot you an email about some next steps in the process. And then you can email us and talk about what you might want this to look like. So Julia has got that link in the chat. There's just a few questions. Fill that out if you're interested. In the meantime, Daniel is going to talk a little bit more about the data that can come as a result of giving these scaffolded formative assessments.
Thanks, Emily. Well, as we know in science, data is everything. So let's take a look at what the data can look like and the insights it provides when you give an assessment on inner orbit. Because all inner orbit assessments are 2 or 3-dimensional. Every question includes either a science and engineering practice, a cross-cutting concept, and like the New York State science tests, which will have both. This allows teachers and admin to look beyond missed standards and actually identify patterns across students, classrooms, and schools. The dimensions report here provides this insight by showing performance across the specific elements of each of the 3 dimensions and allowing you to drill down by grade, school, or class. This helps you target instruction, support learning across multiple performance expectations, and better align your preparation to state assessments like the New York State science tests. Now let's zoom out to a district level view. This is one of my favorite reports because it really highlights why looking at the science and engineering practices and cross-cutting concepts are so powerful. Across the top, you can see the different dimensions, and down the side, you have the different schools in the district. And in the table, you can see the performance across the district. In this example, you can quickly see the differences between schools, such as School 2 struggling with the SEP of constructing and explaining designing solutions, while School 5 is performing much better in that same area. That easy contrast opens the door for meaningful collaboration, allowing for educators to ask what's working in one school and how those strategies can be shared across the district. Now let's take a zoom into the teacher level view and look at student performance on individual questions. So in this example, we can see that the students tend to do well in the 1D DCI only questions and continue to perform strongly on the 2D questions where a cross-cutting concept is added. However, we begin to see a drop when the science and engineering practice is introduced in the other 2D question, and even a larger drop when all 3 dimensions are included in the last question. Because that same SEP appears in both the 2D and the 3D questions, we can identify that as a key area where students need more targeted support rather than unnecessarily reviewing the DCI that they are already doing well on. That's the real power of this data. It helps us move beyond just what students missed to focusing on why they missed it so that instruction can be adjusted with intention. While assessments is a crucial component in helping students prepare for the New York State science tests, InterOrbit also created some more informal sense-making activities to help students practice. I want to share one of those activities with you called the Science that helps with targeting these supports in the classroom and can be implemented right away. In this Science Talks activity, students engage in a facilitated discussion around a novel phenomena, exploring questions, sharing ideas, and collaboratively building understanding. Teachers would select a phenomena from our library, and students will work together to unpack it using all 3 dimensions while they collaborate to highlight the bigger patterns of relationship they notice. It's important to note that this activity is a scaffolded support and not another test. So once teachers see the data to show students are struggling with 3D questions, the next step could be to provide this type of structured sense-making practice in the classroom. And teachers can run science talks at any point of the year to help students become more comfortable making sense of phenomena out loud and together. By practicing this way, when students encounter a 3D question on an assessment like the New York State science tests, it doesn't feel like an entirely new task. Instead, it's the same kind of thinking they've been practicing in class. These science talks promote collaborative sense-making and help students ask better questions and connect their prior knowledge to new concepts as they get prepared for New York State science tests. And this can be a great informal first step for test prep that can be implemented right away. All right, that's all we have planned for today. I'm going to pass it off to Emily to wrap up the webinar.
All right. Thank you so much, Daniel. So just a quick recap, some of the big things that we discussed today. So we talked about the structure and expectations of the New York State science tests and talked about how the dimensions are woven within those items, as well as how you can give scaffolded items to help support students answering these 3D rigorous questions. Remember that students are going to be asked 2D and 3D questions, so we really want to focus on supporting them with the SEPs and the CCCs in order to help them answer those 3-dimensional questions. Also, keep in mind that proficiency is different. When we're looking at the elementary and the intermediate, we're at about that 44-42%. And when we're looking at the regions, we're at about that 60 to 66%. So having that frame of reference change when you're asking them these rigorous 3-dimensional questions can help in seeing if your students are on track towards that proficiency. All right. So again, we've got the interest form link in the chat. This is just letting us know that you're interested in trying out InterOrbit and learning more. You can also follow us on YouTube. We post a lot of videos just like this. And in fact, this recording of this webinar will be on our YouTube channel tomorrow. You can also email us at inquiries@interorbit.com if at any point you want to just ask us questions or get the conversation started. Thank you so much for being with us here this afternoon. It was a pleasure speaking with all of you and having great conversations. And as Hansel has said, may the force be with you. Have a great rest of your day.